So here is another example of maybe a more challenging question from this exam that you might see that you should show your work, or what I'm looking for in your work. This example combines what we've learned about vectors and describing lines or drawing equations for lines, as well as the dot product or cross product, in this case dot product, and using it to solve a geometric problem. The distance between a line and a point off the line. Now, I expect you to draw a diagram of what that looks like, and we'll see that right now. So, a quick picture of the problem is it doesn't have to be perfect. You just draw a line. It doesn't even have to look like it's in 3 space, a point off the line, and a visual description of what the distance should be. So there are a lot of distances between this point and any other point in the line, but there is the closest distance, which I drew with a pink sort of line segment between a point, some random point in the line that I don't really know, but that point is sort of the closest point on the line to the point P that we're looking for. I labeled the equation of the line over here that's given to me in parameterized form. I said this is what D is, the shortest distance between the line and the point P, and I labeled the location of the point P. Now in the textbook, there is a formula that you can just reference to find the distance between the equation and the line. You still have to label the geometric pieces that you need for that formula. It's actually not much work, and I show that out here, but for me, it was easier to derive the formula than it was to look it up, so I just show you how I derived the formula picture-wise in case you wanted to do it that way. The formula does require a vector direction of the line, which I labeled as V over here on the graph. It also requires a point on the line and find a vector describing just some random point, the distance between that random point and the point that we're looking in. So I'm going to just find a point on the line and say this blue vector is the vector from O to P. The nice thing about the formula is that it can, as long as you choose any point on the line, it'll work. So I just choose the easiest point for me to find, which happens to be just from the equation right here of the line. Similarly, any vector along the line or giving the direction of the line will work. Doesn't matter if the scalar is off, if it's flipped from another possible direction vector, it will still work in the formula. So now I've labeled the point I've used for my line and the vector of the line. I can do that because I know how to read the parametric equation and where that information is hiding inside my parametric equation. Using a point off the line and the point I'm interested in, I was able to come up with the component form of the vector from O to P. Now, either I look up the formula from the book and use it, or I start to derive the formula for what I know about cross products and trig. I'm going to start from what I know about cross products and trig, just so you can see how it's derived. And if I look at this line, I see a right triangle where the hypotenuse is the vector from O to P, and the side opposite, which is the distance, is right over here. I remember that hypotenuse times the sine of the angle opposite equals the same thing as this leg length, which happens to be my D. I also recall that there is a magnitude of the there's a magnitude of the cross product that has a sine of that angle involved in it. Without changing inequality, I want to put in a factor that I need for the cross product formula, which happens to be the magnitude of this direction vector V. Because I don't want to change my answer, I also have to divide by the magnitude of this direction vector V. So the numerator of this product is the same thing as the magnitude of the cross product. That's a formula inside the textbook. And we end up getting that the distance between the point and the line is the same thing as the magnitude of the cross product of the direction vector and the vector from O to P divided by the magnitude of the direction vector. This formula is already in the textbook, and you could have just cited that instead of doing the long string of derivations that I did just for your sake in this little video. To be clear, everything above this black line is probably required for showing work, and this box is required for showing work. This sort of intermediate is a bonus extra thing that I just did for your sake. So to continue with the theme of showing your work on this problem, we now have to substitute in those vectors into our calculations. I So I do want to see you do the cross product just to make sure that you know the order of this, as you cross product that you see here, how to substitute it into the cross product and how to compute it. I do want to see how you're calculating the cross product formula, so substitute it in, but once you get to the point where you're doing the arithmetic, you could just plug in the numbers over here. The rule of thumb for deciding what goes into showing your work is that if it's an operation you learned this before this test, it's one that you should show me you know how to do. If it's an operation that you learned in previous classes and at this point I understand that you understand how arithmetic works, you don't have to show me. Similarly, we learned about magnitudes of vectors, so I just want to see how you substitute your components into the magnitude formula. So just substitute the next vector into the magnitude formula, write the approximate number when you punch it into your calculator, and then use the formula to take the ratio of these two calculations and put the approximate distance listed over here, box your